And since this is a general audience, I'll try to be most basic I can. All right. So let me start with a vague question. So suppose that you have a surface with a certain number of poles. So the number of poles is called the genus of the surface. So for example, if the genus is 0, then we're talking about spheres. If the genus is 1, and the surface has the shape of a donut, which we call torus. We can also talk about higher genus surfaces. So you fix one of those surfaces, then you ask the following question. So what is the best realization of such surface into Euclidean free space? So of course, once you fix the genus, you can realize it in many different ways, many different curved shapes in free space, and you want to somehow find the optimal shape a given surface can assume in Euclidean space. So the question is vague, we have to make it precise. But if the genus is 0, there is an obvious answer. The most symmetric, the most beautiful shape the topological sphere can assume in Euclidean space is of course given by a round sphere. So whatever precise sense you make out of this question, the answer for the genus 0 case should be round sphere. So the next interesting case is of course to see what is the best torus. So if you want what is the best donut in R3 in Euclidean free space. The answer here is not so clear, so you have to make it precise with some interesting mathematical sense. So recall that given a surface in Euclidean free space, its geometry is determined by those two numbers, those two curvatures, which in the picture are denoted by capital 1 and capital 2. Those are called the principal curvatures. In order to define them, what you do is very simple. So you pick an orthogonal line to the surface passing through the point P. Then you consider planes passing through the point which contains such line. So each such plane intersects the surface in a curve containing the plane. So that curve comes with the curvature. And as you rotate your plane around the axis, you see different curves, of course, with different curvatures. Then you take the maximum and the minimum curvatures that you see out of this process. They always come in orthogonal directions that are called principal curvatures. So those are very important numbers. And if you take the average of these two numbers, you get the mean curvature, which is a very classic notion of curvature of the surface. So this is the curvature that will play a role here. And then we make the following definition. So suppose you have some closed surface in free space, then the Wimmer energy of the surface is defined to be the integral of the square of the curvature. So that's the definition of the energy of the surface in Euclidean free space. So notice that the square here is very natural because you want this energy to be scale invariant. So you want the energy to have the property that if you multiply the surface by 2, for example, the energy should be the same, right? Because you're only interested in the shape somehow. So this is the square here is to make it scale invariant. Okay. So in the 1960s, Wimmer proved the following results. So we proved that the Wimmer energy of any closed surface, no matter its genus, is always bounded below by 4 pi. And it can only be 4 pi if the surface turns out to be a round sphere. So he made the question, what is the best sphere to size, by looking at the problem of minimizing the Wimmer energy over all such surfaces. That's what he proved in the 1960s. A few remarks. So this quantity is especially interesting from the mathematical point of view because it's invaried by the action of conformal transformations. Those are transformations that preserve angle in R3. So this actually was known in the 1920s by Blasch and Thomson. Very easy to see that the energies are varied by translations, also rotations, and as I said, scalings, but it's also varied by inversions. That's quite interesting. And it also appears in physical contexts. For example, in 1812, Poisson had already reduced the definition of this energy to model the energy of elastic shells in free space. So it appears in elasticity theory. And more recently, it also appears related to the energy of cell membranes in the so-called Elfish model. It's also relevant in physical situations. So let's go back to the question: what is the best torus in R3? So now we already have a precise sense for such a question. What we want to find the torus that minimizes the contribution. So in 1965, Wilmer made a conjecture that's known as the Wilmer conjecture. So he conjectured that the integral of the square of the mean curvature, in other words, the Wilmer energy of any torus immersed in Euclidean space, should be at least 2 pi squared. So if the surface is a torus, he predicted that 2 pi squared should always be lower bound for the Wilmer energy, and it's actually achieved. So there is a particular torus whose Wilmer energy is exactly 2 pi squared. That's a torus of revolution with a circular section. So what you do is you pick an axis of rotation, here represented by the y-axis. Then you pick an orthogonal direction with that one, and then you draw the circle of radius 1, centered at a point of distance square root of 2 from the axis. So the only important thing is that the ratio between these two numbers is square root of 2, right? Because the energy is a scalar invariant. Then you rotate the circle around the axis and you produce this picture. So this is a circular torus which has Wilmer energy exactly equal to 2 pi squared. So somehow Wilmer felt that the minimizer should be a torus of revolution and the section should be circular. Somehow he had this in mind, and then he computed for all such circular to arrive which one was the best, and he realized the best one is the one ratio square root of 2. So that's the conjecture. That torus is the best one. So you might ask the question, why 2 pi squared, right? So why is this number special? In order to answer that question, we have to leave the Euclidean space and go to the three-dimensional sphere. So those two spaces are related by the so-called stereographic projection, which happens to be a conformal map from the free sphere minus the north pole onto the three-dimensional space. So here's the picture. So you might think that there is a light source on the north pole. So for any point on the sphere, this produces a shadow on the base plane, and the shadow is the stereographic projection. So if you have a surface, so this is of course two-dimensional, but you have to imagine the three-dimensional picture. So if you have a surface sitting inside the three-dimensional sphere, you can look at its shadow, or in other words, you can look at its stereographic projection, and then you can compute its Wilmer energy. So if you do that, so you pick a surface in the three-sphere, you take its projection, then you get the following formula. That the Wilmer energy of the shadow surface, which was defined to be the integral of the mean curvature square. Now, if you write it in terms of the surface in the three-sphere, it has this form. So it's the integral of 1 plus mean curvature square, where now the mean curvature is computed with respect to the spherical geometry. So this is the rule to go from surfaces in Euclidean space to surfaces in the free sphere, but those problems are completely equivalent. You can go from one to the other, no problem with that. So the definition here is that if the surface is in the free sphere, we take this form, the Wilmer energy is just the integral of 1 plus mean curvature square, the Wilmer energy of the stereographic projection. So that's the definition that it's important to this talk. All right, so I haven't answered yet why 2 pi squared. So the answer is related to the theory of minimal surfaces in S3, the free sphere. So minimal surfaces are equilibrium shapes for the area function. Those are very interesting objects for geometers, very beautiful. So locally, those surfaces can be thought as the surfaces of solid fields. very easy to produce slope films in Euclidean space, so that you get a sense of what a minimal surface is physically. And there are lots of minimal surfaces in the free sphere. Very interesting. So these surfaces have zero mean curvature, right? So it means that they curve equally in opposite directions. So they provide very beautiful pictures. So you can see that if your surface is a minimal surface, is a critical point in the area, then its Willmore energy just becomes the area. Mean curvature vanishes, so you can see directly from the definition that the Willmore energy of a minimal surface is just its area. So as I said, we know lots of minimal surfaces in S3. For each genus G, there is at least one minimal surface with that particular genus in the free sphere. We don't have a classification yet, but we have lots of examples. The simplest one is the equator. So you have the three-dimensional sphere. If you intersect it with a hyperplane passing through the origin, the intersection is a minimal surface. So that would be a two-sphere with radius 1, therefore its area is 4 pi, which is compatible with the fact that the Willmore energy of round sphere 3 was 4 pi. But the next simplest minimal surface that one can think of is the so-called Clifford torus, which is defined to be the product of these two circles. So you have to choose the radii appropriately so that this falls into the unit sphere. It's very easy to check that this is a minimal surface, very special. And it's also very easy to compute its area. It's just the product of the lengths of the circles. The area is 2 pi squared. And here's the answer to my previous question. It turns out that if you take the stereographic projection of the Clifford torus, what you see is exactly that torus of evolution with ratio square root of 2. So that's the answer. So the 2 pi squared, the Willmore energy of such guy, is just the area of the Clifford torus in the unit sphere. So, okay, so the conjecture was stated in the mid-60s, 1965, and lots of people have made progress on that conjecture over time. So let me give you partial results. So first, in the early 70s, Willmore and independently Shiohama and Takagi, they checked the conjecture for tubes. So you think of, you take a curve in space, a closed curve, you pick the tubular neighborhood of fixed radius, let's say radius r, then the boundary of that neighborhood is called a tube. So for such tori, the conjecture is normally true. Also in 76, Legevin and Rosenberg proved the conjecture if the torus is knotted. So knotted means that the torus cannot be deformed to the standard one, like ambient moves. If you look at this picture, this particular torus seems to be knotted. So if your torus is knotted, then they check that the Willmore energy is already bigger than 8 pi, which is better than 2 pi squared. Then there's an important paper by Peter Lee and Xinjun Yao in 1982. So they checked the conjecture for surfaces which have at least one self-intersection. So if your surface has one self-intersection, then the Willmore energy is already above 8 pi, which is better than 2 pi squared. So if you want to prove the conjecture, you might as well assume that the surface has no self-intersections. We have a word for that, but we can assume the surface is in that. And they also proved the conjecture under some assumptions on the conformal type of the torus, because we got a particular result. Conjecture is also true for flat tori in the free sphere, in agreed by Chen, another class of tori. Here's a beautiful picture. It's also true for tori of revolution. That was proven by Langer and Singer in the work. So now the section does not need to be circular anymore. Think of any plane curve, rotating without an axis, we knew that conjecture would be true in such case. Montiel and Ross improved the result of Li Yao on the conformal type, but it's still a partial result. And that's quite interesting for experimental scientists, because we learned of this after we finished our paper, that these people, Dan Simon and Woods, in 1991, had observed the conjecture experimentally by looking at vesicles with the shape of a torus in the microscope. And somehow the equilibrium configuration is taken by a conical torus. It's gravity of 2, which is some experimental evidence of projection. We also knew that there was one torus which was the best. This is an existence result by being assigned in 93. We just didn't know which torus is that. And finally, Ross in 99 and independently Top in 2000, they proved the conjecture if the torus in a 3-sphere has some symmetry, if it's symmetric under the integral map. So the paper of Ross was very important for our construction. It's kind of like the starting point for our method. Alright, so at this point I will give you the main statement. This is joint work with Neves, as I said. So suppose you have a surface inside a 3-sphere, which is assumed to be closed, embedded, no self-intersections, with genus at least 1. Then the rim of energy is bounded below by 2 pi squared, and it can only be 2 pi squared if the surface in the Kuiper torus, maybe after a conformal transformation is applied. So this is the main theorem of our paper. The paper is available on the internet. It was posted in February 2012. So of course the main theorem implies the Lewis conjecture is true because it holds for Tori, surfaces of genus 1. But not only that, it also establishes the bound, the 2 pi squared bound for higher genus surfaces as well. And it also characterizes the case of equality. Okay. And the proof, as I said in the beginning, uses the so-called Bmax theory for minimal surfaces. So minimal surfaces, remember, are critical points for the area function. Right. Here's the word Bmax. So I'd like to give, in 2 slides, just give some idea of how the proof goes. As I said, we're going to use Bmax method. So let me explain the Bmax method with a very simple picture, finite dimensional picture. So suppose you have a surface shaped like that. This is only a piece of the surface. And suppose I want to find, I look at the height function and I want to find its critical points. So it's very easy to find the minimum point, here represented by C naught, because you can just take or minimize the sequence. So you usually find the minimum point. But it's harder to find unstable points like C1 here. So it's unstable because it has one direction of instability. That means that there is one direction which decreases the function, right? The green line here. So we formalize that by saying that the index of such critical point is 1. The index is just the number of linearly independent directions that produce instabilities. So in order to find this guy, what we do is the following. So we pick some loop going into the hole, like the black loop that I drew here. We look at all such loops. So for each loop like that, we take the highest possible value of the height function. Then you try to minimize that over the class of such loops. So in doing so, you end up approaching the critical point of index 1. So this is a min-max because first we maximize the height function over the loop, then we minimize its number over all such loops. That's the min-max method to find critical points. And an important observation here is that this is a critical point of index 1 in this picture, and we found it using one parameter families. So in general, it's much harder to find higher index critical points because the number of parameters in the family have to match the index of the critical point that you want to find. So if you want to find the critical point of index 3, you need at least a 3-dimensional family. And that's very important because the Kuiper torus as a minimal surface is a critical point of index 5. Okay, so here's an outline, just one slide to give you some ideas. So we start with a surface in a 3-sphere with genus at least 1. We want to prove the Riemann conjecture for such a surface. And the idea is to somehow produce the Kuiper torus by Bmax methods. So we found a natural family of surfaces, 5-dimensional. Here parameterized by, let's say, a 5-dimensional disk. So you think of, you think of the space of surfaces. A point here is just a surface in S3. And there's always this five-dimensional disk passing through your surface. And with the property that the area of each surface in your family is always bounded above by the real energy of the original guy. And the construction is natural. I will not discuss it here, but each surface in the family is obtained from the original one by a geometric operation. So we found this natural 5-dimensional family passing through any given surface in an area bound. And the idea is now that you have a 5-dimensional family, you want to do Mimax with all such families, of the class. You want to find a critical point for the area function, in other words, the minimal surface. So you apply Mimax theory, and then you find a minimal surface produced by such Mimax methods, which are denoted by sigma hat. And because this was a Mimax, the area of this critical point will be below the Wilmore energy of the original guy. Finally, you have to prove that this surface is the Clifford-Torus, and that's the difficult part. So here, very quickly, there are two main ingredients here. So one is a theorem of Codá, which characterizes the Clifford-Torus by its index. It says that if the index is at most 5, then the surface is either the Clifford-Torus or a great sphere. Great sphere has index 1. So then you have to be very careful, because if one could get great spheres in the end, then the whole method would not work, because the boundary would be 4 pi, not 2 pi squared. So we need a key topological argument to rule out the possibility of getting great spheres. And that argument, of course, uses the fact that the genus of the original surface was at least 1. So we rule out great spheres, we conclude that sigma hat is the Clifford-Torus, therefore, finally, the real energy of the original guy is bounded below by the area of the Clifford-Torus, which is 2 pi squared. And doing so, we prove the main theorem and also the real conjecture. So we don't care if the surface is a torus or not. The only important thing is that the genus is at least 1. So just one last slide after so this proves the real conjecture. But after we finish this paper, we realized that our theory could be used for all the problems as well. So I'll just show very quickly. And after we finish the paper, we solved another problem, this time a problem in topology. The idea is that instead of a surface, you think of a link, which is a pair of curves in free space linked to each other. And there was a conjecture of Friedman, Hay, and Wen, which predicted in some precise sense what is the best non-trivial link in Euclidean free space. That's given by the standard Hopf link and its stereographic projections. So we managed to verify that this conjecture is true using similar methods. In other words, we found a connection between the theory of links in free space and the theory of minimal surfaces in the free sphere. All right, I should stop here.